Great, thank you. Yeah, so let's go straight ahead. So I guess just to sort of set the stage, let's first really quickly go across what is and isn't a side effect. So here we have this program where we have these two add instructions that add the inputs, and then there's a bunch of code in between. So the question is it safe to like replace the value of s with the value of r? And the answer is yes, it is. Well, because the mathematical function add only depends on the inputs, right? So one way to think of something having no side effects is that its outputs depend only on the SSA values that are its inputs. For an example of something that is a side effect, suppose we have a memref that we load from, and then we store a value into this memref at that index, and then we load a value again. Now the question is, well, once again, is it safe to replace v2 with v1? Is this a safe transformation to do? Well, it isn't. Because we've stored something in between. Even though if we actually look at the SSA instructions, they're both exactly the same. They both say memref.load, like %a, %i. So in some sense, the way to think about it is that if we have side effects, then the output depends not only on the SSA inputs, but also on like some implicit ghost information that's hanging around, right? So now we have this question of, okay, how do we actually model this implicit information within MLIR? So Jeff?
All right, thanks. So basically, in MLIR, there is a somewhat generic side effect modeling interface. And the core part here is the side effect type. So a side effect in MLIR has three things. It has an effect kind, which is basically a type ID. So this allows you to do LLVM, : ISA, and cast, and so on. And a particular type of side effect will have a particular type ID. A side effect has a resource that it can affect. For example, in memory effects, you can write to global memory, and it goes by a string name. It's also a singleton. Optionally, and typically you don't have both of these, an effect can directly specify an SSA value or a symbol reference that it is affecting. So what happens is that you have an effect op interface, and what all this interface does is it asks the operation, what memory effects do you produce? And it can produce one or more or none side effects. So it's pretty abstract, and all of these are typically base classes that are used to implement a particular kind of side effect model. The most important one in MLIR, at least in upstream, is memory effect op interface. So memory effect, there are four kinds: allocate, free, read, and write. And the resource in this case is still pretty opaque and application specific, but it could be, for example, GPU shared memory, runtime handles, JIT contexts, etc. And what you can affect with a memory effect can be a memref, so an SSA value, or a global variable through a symbol. So if we take the example that Sid showed earlier, we really see load and store effects, and these are loads and stores on an SSA value, and that means MLIR can distinguish loads and stores between different pieces of memory represented by SSA values, almost like handles. So one thing that MLIR does with memory effects is that CSE is memory effect aware. So in the example Sid gave before, it was not valid to CSE the loads because there was a store effect to the affected memory in between. But in this situation, we have two identical loads, the operations are identical, and there are no other affecting operations in between them. So we can just delete it and replace it with the first load. Now, there's another thing that MLIR does with side effects in dead code elimination, which is that it deletes operations with allocation effects where the allocated entity is not used at all. So this is interesting because if you have leak sanitizer running on your program, MLIR has just optimized away a memory leak. And there's some questions as to whether or not this should be allowed behavior, as to whether a memory leak is a side effect to something beyond just the allocation. There's a couple of other things in side effects. One of them is this effect on full region, which I could find no actual references to this in GitHub or on Google. A recently added thing to side effects is the stage. And this is very useful for more complicated operations where there are more than one effects on the same resource within the same operation. So for example, if your operation reads and then frees a resource, it's important to know which one comes first. Another part of MLIR's side effect modeling, and one can argue if this is side effects or something else, is conditionally speculatable. It's a very simple interface, and it's simply pretty much just ask an operation, can I hoist you? And it can be used to model ops with undefined behavior in certain conditions like div. So div is a memory effect-free operation, and it has no side effects, but it can have undefined behavior depending on the dynamic value of its inputs. So in this situation here, it's not valid to hoist the div because the div has undefined behavior, but not in the code as written. So there are a couple of things that are missing in MLIR side effect modeling. One is that memory effects on functions and function arguments would be great. This would allow callers to reason locally about the memory effects of a call. So in LLVM, these are things like read none, read only, and read write. So you can designate a function call as effectively being a no-op and delete them from the IR without requiring interprocedural analysis. The other problem with memory effects op interface is that it tends to be a bit of a black hole for side effect modeling. It's very privileged in the MLIR infrastructure, and this tends to force users into using it to model their not actually memory effects in order to reuse upstream infrastructure. Here's an example from the TensorFlow dialect that has this TF must execute trait, which is effectively put on operations that they don't want DCE to remove for some reason. Another problem with upstream side effect modeling is the recursive memory effects. So what recursive memory effects does is it considers the effect of the operation to be the union of all the effects of the operations inside its regions. What this does is it walks all of the ops in the region and collects the memory effects. The problem here is that if you have a loop with a very large body and say that the canonicalizer changes one op in the body, then the canonicalizer will go back up to the loop op and say, hey, please recompute your memory effects and tell me if you're now side effect free. This is great because that means if you remove all of the side effects from a loop body, that loop itself can now get deleted if its results are unused. The problem is if the loop is very large, you change one op, it rewalks the whole body, change another op, and you get quadratic explosion in compile time.
Yeah, so thanks. So now I guess the thing that I'd like to talk about is, so we have this particular notion of memory effect, which is really cool, but sort of in general, there are lots of notions of side effects that have been explored, and it may be the case that eventually MLR wants to model more and more of these. So there's a question of, okay, how do we model these, right? And the answer is because we're in MLR, we're going to build interfaces. But when we sort of start asking the question, okay, we need to build interfaces, there's a question of what the API is. And sort of the modest proposal that I have is before designing these APIs, maybe we should take a look at some research. And the research is on these things called algebraic effects. So, okay, what are these things called algebraic effects? So the idea is pretty straightforward. So let's suppose we have an imperative program which stores a value val to memory, and then it loads from it. Now, we all know that this can be optimized to say that, oh, we can do store forwarding, and the value should just be x. But sort of the way in which a functional programmer would think about this is that you have these two expressions on the left-hand side and the right-hand side, and they're actually equal. So we don't think of it as a program transformation in functional land, but we think of it as an equality between these two functional programs. So it's called algebraic effects because the algebraic part stands for the equality, and the effect stands for the side effect. So the nice thing is that this is a bunch of research has been done by people that sort of tell us how to design these APIs, what optimizations are possible, what analyses we can do. But sort of the question is, okay, who uses these, right? For example, there's this somewhat researchy functional programming language called Coca. Now, the nice thing is if you look at the page, they say, oh, it makes it really easy to write compilers, it optimizes these things. The downside is, well, they say you just use well-studied category theory and effect typing, right? So this leads to the usual problem of, oh, these are just functional programming people, what are they even doing? So funnily enough, I actually wound up looking for a meme on functional programming iceberg. And I didn't make this, but algebraic effects is right down there at the bottom, right? So, yeah, but the nice thing is that this research is now slowly getting productionized. In particular, the WebAssembly folks are picking this up because in WebAssembly, they want to act as a single common runtime for a bunch of different languages and a bunch of different notions of coroutines and backtracking and things like this. And so WASM has decided to try to use effect handlers as their sort of a common substrate to represent, analyze, and optimize these things. So I would suggest that if we ever want to extend the set of side effects that MLIR has upstream, then maybe we should take a look at relevant research that the functional programming people have done. So, and there's a blog post that I'd like to plug. It's called Algebraic Effects for the Rest of Us. I think it explains these ideas very succinctly and very nicely. So if you'd like to have a look, please go check it out. And thank you. Yeah.